Okay, this lecture is the introduction to the basics of chemical bonding. We're going to go a little bit beyond the standard ionic covalent, and just a little. So to the PowerPoint. Now, I am not going to go into detail about the specifics of ionic and covalent bonds in too much detail, but you can go to the recorded lecture in the review section from the intro class to get an in-depth lecture on that. So the general topics we'll be covering, that shrunk for some reason. There we go. The models of bonding, of course, ionic and covalent, and the gradient that actually exists between them, but also metallic bonding, which I'm going to introduce, but we're not really going to get into. So that's why it's in parentheses. Next lecture, we'll talk about the Lewis structure, the octet rules, and exceptions to it. I'll talk actually a little bit in this about double and triple bonds, and then of course in the Lewis as well. Formal charge and resonance will be in Lewis structure, and a little bit of isomers. And then moving to the Vesper model will be the third lecture, and I will talk about hybrid orbitals. And that might be, and probably will be a lecture in and of itself, would be a fourth lecture. So of course, what is a chemical bond? That is what the force, the energy between the electrons of one atom and the nucleus, or specifically the protons in the nucleus of another atom. Now, if it's a covalent bond, these electrons are shared. If it's an ionic bond, there is absolutely no sharing going on. It is electrostatic interaction between the negatively charged ion and the positively charged ion. And of course, ionic compounds do not exist by themselves. They exist only in a lattice as a formula. So in the individual one, we call it a formula unit. If you write the formula for sodium chloride, 1 sodium, 1 chloride, because it's always the lowest ratio for a formula unit formula, but it never exists by itself. You will not have a single sodium chloride compound. It always exists in a lattice. And in fact, one thing I'm going to talk about is the formation of that lattice often drives the formation of a number of ionic compounds. So why does a bond occur? The whole point of anything in chemistry is lower energy. So when a bond is created, whether it's ionic or covalent, it means that the product of that interaction, that bond, has resulted in a lower energy level. And that is what drives chemistry. So when you have sharing of electrons to complete an octet between two atoms, that lowers the energy of that system. If you have a lowering of energy with charges because they're close enough, they're at the optimal distance with that positive and negative before you get to the repulsion of proton-proton or electron-electron, that also lowers the energy, because if they're too far away from each other, it causes kind of a stress. We call that a higher potential energy. So as we get closer, the potential energy gets lower, and then there's an optimal distance, because if you get too close, you have repulsion from the protons, or the electrons. And the bond type contributes to its chemistry of the compound or molecule, and the physical states and the physical properties, melting point, boiling point, brittle, conductivity, whether it's ductile, means it can be drawn into a wire, or malleable, which means it can be shaped. So all of these are dependent on the type of bond and the nature of the bond that's formed. So of course, the simplest definitions of these is ionic bonding is simply a transfer of electrons, or the ion already exists, the transfer has been made elsewhere, but it's an electrostatic interaction. Covalent is sharing electrons. Metallic bonds involves an electron pooling, and actually when you have metals get together, you actually end up with this sea of electrons. They kind of all float. It's not a sharing or a joining like with covalent, but it's it's a completely different kind of chemistry. It's really, really fascinating. If you take it organic, it's great. But the electrons kind of exist as a pool or a lake, and they can flow. And that's often why we get the conductivity, the flow of electrons. Electron comes in here and it goes off, one leaves at the other end. Now, in bond types, we don't, in intro, we talked about absolutely ionic or covalent, but in fact, that's really not what you have. You have a continuum. You have a, for example, between ionic and covalent, you have a bond that is purely ionic, purely covalent, or a gradient more often, somewhere in between the two, depending on electronegativities. Purely ionic has very, very large difference in the electronegativities of the atoms, and I'll come back to this. Purely covalent is, for example, when you have two of these same atoms, like chloride here, or chlorine gas, bond together. There's no difference in electronegativity because it's the same atoms, therefore, perfect sharing of electrons. They are distributed equally around both atoms the same. And of course, we're still going to stick with the definition of ionic, the general definition with ionic as metal to nonmetal, and covalent is metal, non-metal to nonmetal. So, all right. So ionic compounds exist in a lattice or a crystal. They're very hard. It's a strong bond because you have to break all of those bonds to disrupt. You can't just break one. So the formation of this lattice releases energy. And this is called lattice energy, right? It's always negative because it's always the release of the energy, and that drives the formation of the lattice. And it's dependent on distance between the nuclei. So we'll talk about the lattice energy between, sodium chloride. So sodium, which is large, chloride, which is small. There's a distance between the nuclei and these, this as well and this as well, but also the charge. This is a 1 times 1, positive 1 times minus 1. Here. So lattice energy is proportional to the multiplying the charges on the top and the distance between the nuclei on the bottom. So again, it's very much like our energy, the Coulomb's law, which is energy is proportional to Q1, Q2 divided by R squared. It's the same concept. Charges on top, distance on the bottom. Now, I'm just going to pop to this slide real fast. It's kind of confusing, but I just want to show you a little bit. The Born-Haber cycle is talking about the step-by-step formation of an ionic compound from the gaseous forms. So you get to the gas, this is the theory, you get to the gas form right here. But to get here now, it required energy. I'm not going to even go on this step. And an ionic compound is considered to be formed from the gas state gaining or losing an electron, because it has to be an individual. At this point, we're talking about the individual atom. How can you have an individual atom? It has to be a gas. So that's why these are in gas state. So the next step, it requires energy to change the lithium to take an electron away from lithium, right? Now we have fluorine gas. Now, when you add the electron to fluorine, a little bit of energy is given off. So you've made up a little bit for the energy you needed to create the lithium ion. Now you have two separate ions. These will come together, not individually, but in a lattice here, and the formation of that lattice releases a tremendous amount of energy, and that pays for all of these steps up here, the individual steps that require energy to prepare the ions for their final formation. So this is the Born-Haber cycle, and the biggest take home is just that this is not always favorable. Look, the formation of the individual ions is not favorable, right? But The lattice energy step releases so much energy because it is the final product is such a lower energy level that is what drives the formation, in this case of lithium fluoride. So that's the take home from message from here and why the lattice energy is so important. So when you're asked to calculate the lattice energy, you are going to look at the charge, calculate the greater or the lesser, and the distance. So the greater the charge, the higher the lattice energy, the smaller the distance, which means your smaller atoms, the higher the lattice energy. So if you had to say in this question, which of these has the greatest lattice energy? Well, sodium and chloride are +1, -1. So that's going to be a 1 on the top, right? We're going to look at the top here. Calcium chloride, that's a +2 and a -1, so that's a 2. Same thing here. Sodium oxide, you have a +1 and a -2. So again, that's 2. Calcium oxide is +2 times -2, and so this would be 4. Our number on the top of our lattice energy would be 4 divided by some distance. That is absolutely going to drive the lattice energy of those choices, and that will be the highest lattice energy. So even though there are differences in the sizes, they're not significant enough to overcome the differences of the charges. So same thing here. What combination will have the most negative? The most negative lattice energy means the greater amount of energy released. So we would call it the highest lattice energy released. So you want a high number on top, so you want high charged ions. So it's either C or D, right? But you want a small distance because the smaller your number is, the greater your lattice energies. Inverse relationship. So there's your small distance and high charged ions. And so the answer here is D. So there's your concept for lattice energy. The the bond types contribute to the physical characters of the compound. So ionic compounds are hard because you have to break that entire crystal rigid. The bonds within the ionic bond, think about the covalent bond. Those atoms can move as long as it's just a single bond. They can move. There's rotation, there's flexibility there, but you don't have flexibility with the ionic bond. So they are rigid. They have a high melting point because you have to break so many bonds to get it to go from a solid to a liquid. The ionic compounds do conduct electricity, but not in the solid state. You've got to have a fluid system for the ions, for the electrons to be able to move. The same, so if we go to this picture here, a solid ionic compound, the electrons are fixed. They cannot move through here. You've got to have a fluid system. So molten ionic compound is where the actual crystal is the melted version of the crystal. And the most electrolytic situation is an ionic compound dissolved in water, because in this case, the ions are individually separated by water molecules, and there's a tremendous flow of electrons through this system. When you have a large electrolyte. The reason they're brittle is, again, the lack of fluidity in the bond. A covalent molecule can move, the two atoms, they're still connected. But because an ionic compound depends on the absolute geometry of the positive and the negative to each other, if this is shifted, and it takes a very large force to shift it, you now have a disruption of this positive negative. You end up with positive next to positive, negative next to negative. That is, you're going to get a repulsion, and it's going to fall apart. So it takes a tremendous force to move these, just to move all of them. But because of the lack of the rigidity, the lack of motion between these interactions, it contributes to it being brittle. Now, covalent bonds, of course, are sharing of electrons. And you have the electrons shared, being attracted by the protons in the nucleus of the other atom. And if you have the same atom, you have perfect sharing. And you're going to have the greatest proportion of electrons in a diatomic system, two of the same atoms, in between and directly around the nuclei. And then as we spread out, it gets a little more dispersed. So the highest probability is around the nuclei and a bit away from it, in between the two and around the two. However, there is an optimal distance, and this is the bond length, the distance between the nuclei. Because the closer you get, so you've got the sharing, and so the atoms are getting closer to each other so that the electrons can be shared amongst the nuclei. But if it gets too close, now you've got repulsion between the protons and the two nuclei. So it's lowering energy, but then the energy starts to go up again because now the protons in each nuclei are too close together. And also the closer you get, you also have the repulsion with the other electrons, but primarily it's the nuclei. So you have two atoms creating a covalent bond. They're coming together for the various chemical characteristics, and the energy starts to low the closer they get because the electrons now can share with the proton of the other nucleus. So now we have that positive negative interaction going on. And so you get closer, the energy is lowering, lower energy state. You have an optimal distance where it's lowest. That is the bond length. Because if you start getting closer, now the two nuclei energy level goes up because of the repulsion of the two nuclei. And they will never get too close. There's always going to be, this will go up to infinity. So this distance, this perfect balance, is the bond length. And it is measured, and they're in tables, and we know what the length of each of a standard bond is, of a standard single, a standard double, and a standard triple. And you'll actually later be using these bond energies to calculate in your calculations. So the characteristics of the bonds, a single bond. So we talk about bond energy. That's the energy it takes to break the bonds. That's the potential energy stored within the bond or bonds, and it also can be thought of as the energy it takes to break the bonds. So a single bond is a lower energy, stores lower energy than a double, because right, it's a lot harder to break this, which is lower than a triple. These are also shorter. So a single is longer, a double is shorter, and a triple is even shorter. And again, we know these numbers, they are in tables, you can look them up. So this contributes to how strong this molecule is, right? How hard is it to break this molecule apart? So some examples or some questions here. What force or forces limit the distance between the nuclei in a covalent bond? The distance, the limit means what's stopping it from getting closer. So it's going to be a repulsive force. So that rules these out already. And it's in fact the repulsive force between the nuclei are what limit the distance. They stop it from getting any closer. And in this question, the primary driving force between the formation of covalent bonds, remember, the primary driving force for anything in chemistry is a lower energy level. So it's going to be energy released. So we're going to look for those questions. So it's not energy gained because it's the product. So the energy released, two nuclei are not going to attract each other. Two electrons are not going to attract each other. So it's when the nuclei are attracting the electrons. You have the positive here and the negative here. You get that attraction, the energy is released, and they get to a perfect balance. Again, the nature of a covalent molecule, the bond of a covalent bond, contributes to its physical properties. They have lower melting and boiling points because since these covalent molecules are able to exist as individuals, the only thing you have to break is the interaction between the molecules, the intermolecular forces, which we are also going to go into later on this lecture. So these are lower energy than an ionic bond. So these are easier to disrupt and therefore change the phase of your covalent molecule. However, you can have very strong solid structures that are covalent, because if you have a number of them, you get the covalent structure of sharing. And once again, like ionic, you have to break the whole structure. So you can have very, very strong, hard, solid structures of covalent, depending on how it's listed. Okay. So we talked about there's ionic and there's covalent, but in fact, it's not quite that cut and dry. Now you learned about electronegativity and sharing of electrons. And then if you have the two identical atoms, you have perfect sharing. But that is the only time you have perfect sharing. Most often you have an unequal sharing based on electronegativity. And of course you have the dipole moment. So when you have this, you get what's called a polar covalent bond. It's a covalent bond, but it has a polarity. More of the electrons are around one of the atoms than the other. It's still shared, but it's not shared equally, and you have a dipole moment. And the dipole moment can also be calculated, and again, like all the other forces we've been talking about, it's dependent on the charge and the distance. So I'm not going to ask you to calculate a dipole moment, but once again, just recognize, like everything else, it's related to the charge and the distance, but this time it's direct. It's not an inverse relationship. So the difference in your electronegativity depends on the level of polarity. Fluorine, of course, is the most electronegative atom. It has the greatest affinity for electrons. And anytime, unless it's bonded with itself, it's going to pull the electrons towards it. And so that's what contributes to this gradation in the bonding of something having, and we call it having greater ionic character or lesser. We compare it to the level of ionic character. That means the more polarity you have, the greater your ionic character. And we have a way of measuring this. But this is a picture from my old Mortimer, which is why it's so funky looking. But this is a pure ionic bond, right? Down here we have a pure covalent bond, where it's perfectly shared. But now we start to introduce polarity, and now you have a disruption in the shape of it and the distribution of electrons, and you have a polarized covalent bond, or a polar covalent. And ions, in fact, can also have distortions where you get an uneven pull. So this is a distorted ion. So there's a visual of the gradient. We calculate the difference in the electronegativities between two atoms, and that is graphed to tell you the percentage of ionic character. So you want to know how to determine if something has a low ionic character or a large ionic character. And this will be determined by their electronegativity. So you subtract the electronegativity of two atoms. So let's look at hydrogen is 2.1, fluorine is 4.1, so that would be 2.0 is your difference. And we come over here to 2.0, and that's way up here. It's about 65 or 70% ionic character. So that's actually very ionic. It's still a covalent bond, but it's a polar covalent. So any difference in electronegativity that is greater than 1.7 is mostly ionic, which means it's more than 50% ionic. Less than 0.5, so let's go to our table and look at, I don't know, sulfur and phosphorus, if we have a compound there, or how about carbon and sulfur? We get that a lot. Carbon disulfide. That is a difference between 2.5 and 2.4. It's only a difference of 0.1. So that is actually way down here. We would call that almost a purely covalent. So a difference in electronegativity that is less than 0.5 is almost purely covalent. And between 0.5 and 1.7, we call that polar covalent. And as you see, there's a different levels. So you want to be able to say if something is more ionic character or less ionic character. So here's an example. You have hydrogen bonded to 4 different nonmetals. They're all in the same period. So if we follow the electronegativity trend, electronegativity decreases as we go down, increases as we go up. So the least polar bond should be the one that has the lowest difference in electronegativity, hydrogen iodide, because iodine of fluorine, chlorine, bromine, and iodine is the largest, is further down, and sure enough, that's 2.2 versus 2.1. That's only a 0.1 difference. It's almost purely covalent. So that is the introduction to the polar covalent, ionic character, and the gradation in between the two. It's no longer purely ionic and purely covalent. Okay, so the next lecture I'm going to start talking about Lewis structures and formal charge and resonance and fun things like that. As soon as I can get this.